The next speaker up is Rocky Kolb. Rocky Kolb is a cosmologist working in a wide variety of subjects in the interface of particle physics and cosmology. He is the Arthur Haley Compton Distinguished Service Professor of Astronomy and Astrophysics at the University of Chicago. From 2006 to 2012, he was chair of the department, and since 2013, he has served as the Division of Physical Science Dean. He's also a member of the Enrico Fermi Institute and the Kavli Institute for Cosmological Physics. He received his PhD in 1978 from the University of Texas, Austin. He did postdoctoral positions, including work with Willie Fowler at Caltech, and he had a J. Oppenheimer Research Fellowship at Los Alamos before he came to Fermi National Accelerator Lab in 1983. Rocky Kolb has deservedly won several notable honors and awards, all of which I will fail to mention, and instead I will reflect on what the experience I had with the good fortune of serving simultaneously with Rocky as a member of the APS Division of Astrophysics Executive Committee, which is a great opportunity for me to see Rocky in action, bringing both his deep scientific insights and his legendary good humor to the sometimes grinding task of that group for the benefit of the entire scientific community. Today, Rocky will talk about baryogenesis, one of the key remaining unsolved mysteries. Please welcome Rocky Kolb.
Thank you, Corbin, for that long introduction. In the brief time remaining, I will talk about the connections between the standard model of particle physics and the and baryogenesis. And I said baryogenesis at 50 years. I don't know when exactly to date the origin of baryogenesis, but one particular paper that was 50 years ago to cosmological accuracy was an often quoted paper by Andrei Sakharov on the baryon asymmetry of the universe. And it's often said that in this paper, Sakharov puts down three necessary conditions to start with a baryon number of 0 and generate a baryon number by dynamical processes. And the three conditions are baryon number violating reactions, that's clear in the paper, C and CP violating reactions, that's clear in the paper also, and a departure from thermal equilibrium that is sort of mentioned in the paper, but it's not so clear in the paper. As a cosmologist, I'm required to start with a slide like this, and there's a lot we can learn about this. We can learn that the early universe was radiation dominated, but today radiation contributes a small fraction of the mass and energy in the universe. We can learn that chemistry is not important. The chemical elements, by which I just refer to elements other than hydrogen and helium, make up a very small fraction of the mass and energy in the universe, much less so than neutrinos. Stars that astronomers love is a small fraction. Most of the baryons, most of the normal matter in the universe is in a hot gas of hydrogen and helium that comprises about 4% of the mass and energy in the universe, and 95% of the universe is dark matter and dark energy. Well, it's usually said that 95% of the mass and energy in the universe is mysterious, but the chemical elements would not be here without a baryon asymmetry. Stars would not be around without a baryon asymmetry. And hydrogen and helium gas would not be around without a baryon asymmetry. Since we don't understand the origin of the baryon asymmetry, I think it's fair to say that 99.825% of the mass and energy in the universe is mysterious. So I'd like to just have two slides about precision measurements of the baryon density in the universe today. The most precise measurements come from measurements of the anisotropy of the cosmic microwave background radiation. Increasing the baryon component in the baryon photon fluid decreases the sound speed of the fluid, which decreases the size of the sound horizon at recombination. The sound horizon is the maximum distance a sound wave could travel before recombination. So if you decrease the size of the sound horizon, these peaks in the anisotropy go to smaller scales, larger values of multipole moment, and you can see as the baryon density increases, the drift of the peak to smaller scales, to larger L. A more dramatic effect is due to baryon loading. As you increase the baryon fraction, as the regions collapse, they would collapse further, leading to a larger increase in the temperature fluctuations. And as they expand, they would not expand so far, and the compression peaks, which are the odd peaks here, will increase. The rarefaction peaks decreases. So it's easy, this is a very precise way to determine the baryon fraction. And the most recent result from the Planck satellite is that omega b h squared is known to very good accuracy, the numbers there, think of 0.02. This is also consistent with the traditional way of determining the baryon asymmetry from Big Bang nucleosynthesis. Increasing the baryon component in the baryon photon fluid leads to an increase in the baryon to photon ratio eta. In nucleus statistical equilibrium, the NSE abundance of a species is proportional to eta to the A-1. So deuterium, helium-3, and deuterium and tritium are built up slightly earlier, leading to an earlier generation of helium-4 and building up more helium-4 at the expense of deuterium, helium-3, and tritium that's left unburnt. So the most sensitive determination is deuterium, and this picks out a range in eta, the baryon to photon ratio, which corresponds to a region of omega b h squared. So the combination of CMB observations and determination of the light element abundance give us very good information on the baryon fraction today. So this leads to questions. We know what the baryon asymmetry is. Why is there an asymmetry between matter and antimatter? There are various explanations, including going to initial conditions. If you think it's an initial conditions, you require apparently a causal initial conditions. And inflation, which seemingly evades acausal issues for the density perturbations, would dilute the pre-inflation baryon number by an exponential amount. So initial conditions are not a very satisfactory explanation. The modern perspective is that reheating after inflation produced a symmetric universe with equal abundances of matter and antimatter, and the baryon asymmetry developed dynamically after inflation and reheating through a process known as baryogenesis. And the question that we have to answer is, how did this happen, and why is the baryon asymmetry about 10 to the minus 10? So this is an obvious inner space-outer space connection. A complete standard model of particle physics arising from laboratory experiments and beautiful theoretical ideas should be applicable to the universe beyond terrestrial laboratories, and in principle allow the calculation of cosmological parameters such as the baryon number of the universe. The failure of today's standard model of particle physics to account completely for the observed universe, dark matter, dark energy, inflation, and baryogenesis, points to the fact that today's standard model of particle physics is not the final standard model of particle physics. And then there's information flowing in the other direction that cosmological considerations may point to directions for physics beyond today's standard model. And the baryon asymmetry is an example of this. So, can the standard model of particle physics explain a tiny number in the standard model of cosmology? And I will argue that the answer is no, or at least not yet. Can the standard model of particle physics explain an order unity number in the standard model of cosmology, the ratio of the dark matter density to the baryon density, which is about 5.3? These are important numbers, and the answer to both of them is that they cannot be explained by the standard model, at least not yet. So let's ask the question, starting after inflation and reheating, with the symmetric universe, how much the standard model be augmented to produce an asymmetric universe? Now, if you do a Google Scholar search for baryogenesis and leptogenesis, you pull up thousands of papers and thousands of ideas. I cannot discuss more than a couple of them today, and I have chosen to start with electroweak baryogenesis. This is a meeting on the standard model. Then talk about thermoleptogenesis, gut baryogenesis, afflectine baryogenesis, and spontaneous baryogenesis. And there are many, many other possibilities. I could have listed hundreds here that I won't talk about because I don't like them. All right, so let's look at the Sakharov criteria in the standard model. Well, the first thing we need is baryon number violating processes. Are there baryon violating processes in this standard model? Well, not perturbatively, but there are non-perturbative violations of baryon number. And I'll note that these conserve B minus L, and at zero temperature, the 't instanton leads to baryon number violation, but the decay rate or the interaction rate is suppressed by e to the minus 16 pi squared over g squared, which is a very small number. But it was realized that at high temperature, it's possible to have quasi-particle known as sphalerons, and the decay rate above the electroweak transition in the symmetric phase is unsuppressed. The interaction rate would be just alpha weak t to the fourth. And below the electroweak phase transition in the broken phase, the sphaleron rates are suppressed essentially by e to the minus energy of the sphaleron divided by the temperature. And the energy of the sphaleron is mw over alpha w. So there is non-perturbative baryon number violation in the standard model. So the first one is a check. For C and CP violating processes, yes, in the standard model, but this looks to be too small for baryogenesis. You can look at the Yarlskog invariant, that's very small. So there is direct CP violation in the standard model, but it seems to be too small. Non-equilibrium conditions, is that present in the standard model? So let me peel back a little bit about the statement of non-equilibrium conditions, which were not well explained in the Sakharov paper, but was elegantly explained in a paper by Dimopoulos and Susskind in 1978 or so, proving that in the thermal bath, the average baryon number, if CPT is conserved, then in thermal equilibrium, the baryon number must be 0. And it will turn out that in the standard model, this condition is not met. So let me talk a little bit about electroweak baryogenesis. And the idea of this is that the baryon asymmetry is generated at the electroweak phase transition from the seed that's planted by CP violating interactions of particles scattering at the Higgs field bubble wall. So there is an assumption that there is a first order electroweak phase transition, and bubbles of the broken phase are nucleated in the symmetric phase background. And this phase coexistence will lead to non-equilibrium conditions. There is a primordial plasma that consists not only of electrons and baryons and photons, but also all of the quarks and all of the leptons. Outside of the bubble, you're in the symmetric phase. The vacuum expectation value of the Higgs field is 0, and there's a bubble of true vacuum where the electroweak symmetry is broken. The broken phase expands into the unbroken phase. Eventually, the bubbles coalesce and the transition is completed. In the broken phase, sphalerons are suppressed, baryon number violation due to sphalerons are suppressed by exponentially, while in the symmetric phase, sphalerons are unsuppressed. So there is this is an example of a bubble wall that is evolving into the symmetric phase. Inside the bubble, the baryon number violating reactions are much smaller than the expansion rate. Outside of the bubble, the baryon number violating reactions are much larger than the expansion rate. Something that doesn't show up well in this PDF version is the wall thickness that's here, where the vacuum expectation value goes from 0 outside the wall to some non-zero value inside the wall. If there is CP violation in the Higgs fermion interactions, there will be different transmission and reflection of left and right-handed quarks at the wall that leads to a CP asymmetry at the bubble wall. So if I look at the CP asymmetry, it's one term, it's one sign on one inside the bubble and another sign outside of the bubble. Sphalerons violate baryon number violation, and if they interact with the left-handed quarks but not the right-handed quarks, so the CP asymmetry outside of the wall, where sphalerons are effective, convert the CP asymmetry to a baryon asymmetry in front of the wall, and then the baryon asymmetry diffuses into the wall, into the broken phase. So that would be the simple idea of electroweak baryogenesis. Maybe not so simple, it's the idea of electroweak baryogenesis, but there are problems with this scenario. The first problem is that the phase transition in the standard electroweak theory is not first order. You would require a Higgs mass smaller than 72 GeV for the electroweak phase transition to be first order. For larger Higgs models within the larger Higgs masses within the standard model, it is a crossover transition. Another issue is that CP violation is too small in the standard model. And there's also another issue that can come up is that the wall velocity may become too large, and as the wall velocity becomes too large, the wall moves too fast for the baryon asymmetry to be produced and to diffuse into the broken phase bubbles. So the bad news is electroweak baryogenesis doesn't work within the standard model, but the good news is it may point to directions beyond the standard model. So we can ask, how far beyond the standard model does one have to go to have the phase transitions first order? The minimal supersymmetric standard model initially was promising if there's a light right-handed stop, but increasingly stringent LHC conditions challenge this idea. Challenge is a generous word to put here, and another word might be rule out, but some people get upset, so I'll just say challenges the idea. The next to minimal supersymmetric standard model is more promising since there is an extra singlet scalar field that can strengthen the phase transition. You can also extend the standard model by having two Higgs doublets. Two Higgs models are hard to make work since these models that might work have very large Higgs self-coupling. The most promising and simplest approach is to add a singlet scalar, S, coupling to the Higgs. And I will examine that model a little bit. So we can just add a singlet scalar field S, coupled to the Higgs by this term, and this adds a finite temperature part to the potential that will be cubic in the Higgs field and can lead to a first order phase transition. There's been a lot of papers and work probing models for first order phase transitions and the signals this might have at the LHC and future colliders. And I'll also talk about the possibility that a sufficiently strong first-order phase transition at the electroweak symmetry breaking can lead to observable gravitational waves. There's been a series of papers talking about this. I'll just show the paper by my colleagues at Chicago. And what they did was to start with the real scalar singlet field. You have to have the mass of this field larger than half the mass of the Higgs, otherwise it would contribute an unacceptable amount to the invisible decay width of the Higgs. And if the scalar field is too large, its effect on electroweak baryogenesis will be insignificant. So this mass has to be somewhere less than about a TeV and greater than half the Higgs mass. And let's just take a simple model where it couples to the Higgs through the Higgs portal. So there will be 1, 2, 3, 4, 5 new parameters, the coefficients of these potential. And Wang, Long, and Wang did a calculation where they sort of looked at various values of the coefficient and found regions of the space, of the parameter space, where there's a first-order electroweak phase transition. And in this graph, what they show is the departure of the Higgs-ZZ coupling, 1 minus the Higgs-ZZ coupling divided by that in the standard model, as a function of the departure of the Higgs, the HHH coupling, divided by the standard model. So the standard model results here would be 1, and down here at minus infinity. So the orange points, which are sort of, they looked at, I think, 5,000 models. The orange points, which are hard to see because they're covered by other color points, there's a first-order phase transition, but the first-order phase transition is too weak for successful electroweak baryogenesis. The blue points would lead to a first-order phase transition where one can have viable models of baryogenesis. And the red points here will be viable models of baryogenesis, plus the first-order phase transition is strong enough to lead to detectable gravitational waves. So there are many models with detectable values in, say, the high luminosity LHC program here, these red points, which would also result in a detectable gravitational wave signal in E-LISA. LISA is the laser interferometric space antenna. I think the E, it used to mean European, then it meant extended or enhanced. I think of it as expensive. This is the expensive version of LISA, which will launch in 2034. They're quite sure of that schedule. I always ask if that's calendar year or fiscal year, but I never get an answer to that. But in E-LISA, this is the expected limit on omega gravity waves over h squared. And here, these models are plotted here with the spectrum. So all these blue points are thousands of models. There's blue regions of thousands of models here. The orange is down here. That's not detectable. But these red curves are models here that have a first-order phase transition that is strong enough for electroweak baryogenesis and leads to detectable gravitational waves. So an interesting thing here is that many of the models that in principle would be discoverable at, say, the high luminosity LHC here would also be discoverable by gravitational radiation. And the same qualitative results happen to other models. You can impose a Z2 symmetry and have the new scalar field not have a vacuum expectation value. Add a scalar doublet that's quark-like. You could add new fermions other than scalars. All of these lead to significant deviations in the HZZ coupling and large order 1 deviations in the triple Higgs coupling, deviations from the standard model that in principle are discoverable at future colliders. Here there are various future colliders here that show what the prediction would be. If it's a very strong first order transition, it leads to detectable gravitational waves. And the gravitational wave calculation is complicated and interesting. Gravitational waves can be produced by collisions of the bubbles if the first order phase transition is very strong. Propagation of sound waves in the plasma lead to gravitational waves. And there's also the possibility of the production of gravitational waves by the decay of magnetohydrodynamic turbulence. The calculations are difficult, and if you go to enough astrophysics seminars, you know whenever you see the phrase magnetohydrodynamic turbulence, you know don't trust the results of the calculation. How far beyond the standard model do you have to go to have sufficient CP violation? Well, there were ideas that the CP violating phase in the Chargino mass matrix in the minimal supersymmetric standard model would work, and again, increasingly stringent LHC constraints as well as electric dipole moment constraints are a problem. The next to minimal supersymmetric standard model is more promising. The extra singlet provides new sources of CP violation. Same thing's true for non-standard model singlets and multi-Higgs models. So within the standard model, it appears that the CP phase is too small, but going beyond the standard model, you have the possibility of extra phases. And the CP violation may not be a problem. So electroweak baryogenesis doesn't work in the standard model, but it's sort of tantalizing that the ingredients seem to be in place. We need another source of CP violation in evading flavor-changing neutral current limits, EDM, and other constraints. To have the phase transition first order couple light-ish fields to the Higgs, which induces non-standard model couplings, which can be probed at colliders, and sufficiently strong first-order phase transitions could produce gravitational waves. Many aspects of the calculation are difficult: the wall velocity, transport equations across the wall, gravitational wave production, etc. It's a very rich and complicated and interesting idea. Let me turn now to the second most popular possibility for the generation of the baryon asymmetry, and this goes by the name of thermal leptogenesis. Thermal leptogenesis has its origin in the type 1 seesaw model, where neutrino masses and mixing enlarges or accommodated by enlarging the standard model to include a Majorana neutrino with a large mass which couples to the standard model lepton and Higgs. There's a large Majorana mass and a smallish Dirac mass generated by the electroweak Higgs mechanism. And the seesaw results in a light neutrino mass of about 0.3 electron volts. It depends upon the coupling constant and the mass of this heavy field N. So in the standard implementation of this, you want a mass of the N of about 10 to the 12 GeV. The N decays to standard model leptons and a Higgs, and since the N is a Majorana particle, its decay will violate lepton number by plus or minus 1 unit. So you can have the N decay to a lepton and a Higgs, or an anti-lepton and a Higgs. Now, if we assume there's CP violation, and say the decay of the N to an anti-lepton is greater than the decay to a lepton, in the decay of the Higgs, in the decay of the N, you will produce a lepton asymmetry if there is non-equilibrium conditions, and I'll return to this in a moment. This produces a lepton asymmetry, and the lepton asymmetry will be converted to a baryon asymmetry by the interactions of the sphaleron. The sphaleron destroys B plus L. It will send this equal to 0 since sphalerons are unsuppressed in the symmetric phase, but it conserves B minus L. So if you start with an initial lepton asymmetry that's non-zero, produced, for instance, by this decays, and an initial baryon number that's 0, you would suggest that you would end up with a final baryon number of minus 1/2 the initial lepton number. Actually, it's closer to 1/3. For thermal leptogenesis, you also require CP violation, and this requires interference between the tree amplitude and loop corrections in N decay. And the lepton number generated in the decay is proportional to a CP parameter epsilon 1, where 1 would be the lightest N that's decaying. This would be the definition of epsilon 1. It's the square amplitude of decay to antiquarks minus the antileptons minus the square to leptons. And within the type 1 seesaw model, this can be expressed in terms of the Yukawa couplings that's in the model. And here, this can be related to M1, the mass of the N, and M3, which is which is the mass eigenstate. So it's a way to express CP violation in terms of microphysical parameters. Now, if it is a completely out of decay equilibrium, only drift and decay, then the baryon to entropy ratio would be about 10 to the minus 2 times epsilon 1. You require non-equilibrium conditions in thermal leptogenesis, and you have to worry about the possibility that the N decay products and the lepton asymmetry will thermalize. If the temperature is large enough, you can wash out the lepton number through processes like inverse decay, where a Higgs in the thermal bath will interact with the lepton, producing an N. This is delta L equal plus minus 1 reactions. You can have 2-to-2 scattering through an intermediate Higgs, presumably most important going to a top. Or you could have delta L equal plus or minus 2 reactions where a lepton can scatter with the Higgs through an intermediate N going to antileptons, where you would change the lepton number by plus or minus 2 units. The efficiency of the washout depends upon the competition between these reaction rates, and which is a function of the model parameters and the temperature, and the expansion rate h, which is roughly the temperature squared divided by the Planck mass. So we can take a look at these rates. The rates for inverse decay is the rate for decay times the equilibrium number density of N divided by the lepton density in equilibrium. And for the 2-to-2 processes, which violate the lepton number by 1 unit, it's a similar expression. And both of these are proportional to e to the minus m1 over the temperature. If the temperature enters, because you have to have a large enough center of mass energy in these reactions to produce an N, and you also have to have a sufficient energy in the bath, temperature in the bath, to have the N present for these reactions to occur. The 2-to-2 reactions are all with light particles, so this does not depend exponentially on the mass of the N divided by the temperature, and it can be related to the RMS value of the light neutrino masses. The decay rate is given here. Again, it's related to the model parameters, and the 2-to-2 processes are also expressed in terms of microphysical parameters, including the RMS value of the neutrino masses. So interesting constraints on neutrino sector parameters in thermoleptogenesis. The condition for M1 to decay out of equilibrium is that this parameter M1 tilde, which is not directly observable, but it's bounded by the lowest mass eigenstate, and the highest mass eigenstate must be smaller than about 10 to the minus 3 electron volts. And the bound on the RMS neutrino mass to avoid washout by the two-body scattering, delta L equal 2 reactions, is that the RMS neutrino mass must be smaller than 0.3 electron volts. So these are interesting limits on the type 1 seesaw mechanism, and in principle, this thermal leptogenesis idea could be shown to be wrong if either of these conditions fail to be met. Leptogenesis is beyond the standard model, but it's well motivated by observation of neutrino oscillations and masses. Also, the massive right-handed N fermions are present in grand unified theories beyond SU5, for instance, SO10. This scenario has all the necessary ingredients to generate a baryon number, lepton number violation from N decays, followed by B violation from sphaleron conversion to a baryon asymmetry, CP violation from complex Yukawa couplings, and out of equilibrium decay for reasonable model parameters. Experimental proof of the Majorana nature of neutrinos, say neutrino observation of neutrinoless double beta decay, would give a big boost to this scenario. And there's this connection between the baryon asymmetry, which is one number, and the richness of type 1 seesaw models. Let me turn now to gut baryogenesis, because this really set the framework of our understanding of generation of a baryon asymmetry. There was an explosion of interest in the late 1970s after Georgy Glashow's 1974 SU5 paper. In 1978, Yoshimura used 2-to-2 scattering processes to try to generate a baryon asymmetry, but he missed the key idea that you must have a departure from equilibrium, so this doesn't work. Toussaint, Treeman, Wilczek, and Z, and Steve Barr pointed out the problem. Demopoulos and Susskind used or suggested an out-of-equilibrium decay mechanism, and Weinberg and later Yoshimura made quantitative calculations based on the out-of-equilibrium decay. The full Boltzmann reaction network, including inverse decay, 2-to-2 processes, et cetera, were elucidated shortly thereafter, and the applications to SU5 and SO10 grand unified models with including all the reactions there, were done in 1982. So grand unified theories are beyond the standard model, but they embrace the theoretical underpinnings of the standard model, spontaneously broken gauge theories, fundamental quarks and leptons, et cetera. So I hear people say gut baryogenesis is far beyond the standard model, but the ratio of the energy scales may not be the most useful metric to discover how far beyond the standard model. Since grand unified theories embrace all of the theoretical underpinnings of the standard model and really introduce nothing new, it's not that far beyond the standard model, at least conceptually. So gut baryogenesis is a theoretical motivation. There's a theoretical motivation to unify strong and electroweak interactions. And Corbin is closing in on me. So what I will do is to skip gut baryogenesis, which I really love. I won't have time to talk about the Affleck-Dine baryogenesis mechanism other than to point out it involves a scalar field and an evolving scalar field. And generates baryon isocurvature perturbations, spontaneous baryogenesis. I have one slide on it I won't talk about, so I'll jump to the conclusions. The standard model of particle physics alone, combined with the standard cosmological model, cannot explain the baryon asymmetry, at least not so far. Perhaps the answer will come from completely non-standard cosmology or from physics way beyond the standard model. For instance, the TOE, the theory of everything. Well, some people call it the theory of everything, but we had a tweet this morning That said, it's actually the theory omitting evidence, which solves huge problems by pure thought without making boring, testable predictions. Who needs observational verification? Sad. Experiments are for you losers. Make astrophysics Greek again. Or perhaps cosmology is pointing to directions beyond the standard model, electroweak baryogenesis or first-order phase transitions. Perhaps it's pointing to new scalars coupled to the Higgs and new sources of CP violation. Thermoleptogenesis explores BSM physics in the neutrino sector. Gut baryogenesis uses the concept of unifications of forces. So we don't understand the origin of baryogenesis now, but we can hope for disruptions, both experimental and theoretical. Great new theoretical ideas in cosmology or particle physics are certainly welcome. Unexpected discoveries in particle physics and cosmology are welcome. Discovery of low-scale SUSY would open new possibilities for electroweak baryogenesis, also be very surprising. The discovery of non-standard model Higgs couplings at colliders could mean the electroweak transition is first order, pointing to electroweak baryogenesis. Evidence for a non-minimal Higgs sector could affect the electroweak phase transition and introduce new CP phases. Observations of non-standard model sources of CP violations, say a large neutron electric dipole moment, would be a disruption. Proof that neutrinos are Majorana particles, as an observation of neutrinos double beta decay, would give impetus to thermoleptogenesis. Observation of proton decay would be evidence for perturbative baryon number violation at gut scales, and perhaps we should re-examine the possibility of gut baryogenesis. There's also hope for disruptions from the cosmological and astronomical side. Observation of a stochastic background of gravitational radiation with E-LISA could be evidence for a first-order phase transition related to baryogenesis. I didn't have time to talk about baryon isocurvature component in the perturbation spectrum, but this might suggest a rolling field, as in the Affleck-Dine of spontaneous baryogenesis idea. Finally, observation of primordial magnetic fields might point to a role of that in baryogenesis. So that's what I have to say. Thank you very much, and thanks for the invitation. And I'll just leave up some thanks to collaborators and people I've benefited from. Thank you.
Thank you. I think we have time for maybe one short question. I think there's one at the back there.
Not Peskin.
So I wanted to ask you, do we have this? I wanted to ask you about the observation of the first-order phase transition through gravitational waves. This first-order phase transition takes place everywhere. It has broad spectral dependence. There are no spectral signals. It's just noise. You emphasize that it involves magnetohydrodynamic turbulence, so we can't calculate the magnitude of that noise very well. We just have to observe excess noise above background. So some theorist has to swear in blood that the background, or rather the foreground, is sufficiently small. Could you comment on this? It doesn't seem to be very robust.
Right. Well, discovering a stochastic background, essentially noise in the detector, is not a great way to look for new physics. You know, we all want to look for a peak in something that we see. But one thing, and the magnitude of and sort of the details of the spectrum are model dependent. The magnetohydrodynamics contributes, but it's not thought to be the dominant contribution, which is lucky. But one thing that's pretty robust is the peak here, and the frequency peak, which is just sort of the size of the sound horizon around the electroweak phase transition redshifted to today. So that is one thing you can pick out, but it's tough to do. So I think just seeing a stochastic background is not going to tell you, aha, the electroweak phase transition was first order, but it would be interesting if we see departures from the standard model Higgs coupling that you need for a first-order electroweak phase transition, and coupled with the detections by ELISA. So I agree with you, partly.
Great, thanks. Let's say I thank Rocky again for a great talk.